Okay. Um, Now,
It's a
oh,
little better.
let's see if I'm recording. Okay, I'm recording. Um, okay, so first let's have a full look at the board. What's there? Um, yeah, but it's still bad.
It's
Um,
better, but it'll probably get worse.
okay, and then we'll see what happens when I switch to the next board since the view will be different. We'll see if that's any better.
Okay.
Okay, but at least the video is good. So, and that's working. Alrighty. Sorry. um, okay, so we do forward substitution, which is really, as just like even before pivoting, it's the effect of applying all of the operations, all the row operations, to the right-hand side. First the row interchanges, and then the other row operations. Um, and then the last stage is exactly the same as before pivoting. It is back substitution, where we solve ux is equal to y. So that part is no different. Um, so, um, so really the only effect is you're applying the row interchanges to both sides. Okay. Um, so, um, so next one I'm going to do is step through an example where we see what happens with the LU factorization when a situation comes up where it's absolutely necessary to pivot. Um, okay, so once I fill up the next board, we'll see if that looks any better.
It looks the same so far, so that's good.
Okay, well, I'm curious to see what happens when I write on it.
Well, it seemed to be working better now that we've disconnected and connected back.
Oh, okay. Well, that's
Yeah.
encouraging. So, okay. Okay. Leah, time to pan. Okay. Okay. So you're out of practice because last semester we had to do it for you. Okay. All right. So the matrix we'll work with is this one. 4, 7, 2, 8, 5, 3, 6, 9. Okay. Now, this matrix is invertible. However, in this case, it's actually possible to tell almost just by looking that this matrix does not have an LU factorization. That something's going to go wrong when we perform Gaussian elimination. And the way you can tell is by looking at the principal minors. So the leading principal submatrices, there's this one, just a 1 by 1 entry. That part is fine because it's non-zero. And then you look at this 2 by 2 matrix, so upper 2 by 2 block. What is it about that 2 by 2 block that will cause this matrix to not have an LU factorization? Yes, that this 2 by 2 block is singular. So if you compute the determinant 1 times a minus 2 by 4, the determinant is 0. So our first minor is 1, our second minor is 0. So at some point pivoting is going to be necessary. So we can tell that up front, but or if you can't tell that up front, it's kind of a pain to compute all these determinants. We can just go through Gaussian elimination, and at some point we'll bump up against a 0. Okay, so what happens is using Gaussian elimination to work on the first column, we have our first row operation, and it's important during this example to keep track of the multipliers as we go, because then you can see what happens as a result of pivoting. First, our second row is equal to itself minus twice be first row. So that's to eliminate the 2 there. Then the third row is equal to itself minus 3 times the first row to eliminate the 3 in the 3, 1 position. So as a result, here's what we have. Our row operations, we have a unit lower triangular matrix and these multipliers. So minus 2 for this entry and minus 3 for this one. Applied to A, the original A, gives us the new A, which I'll call A2. And what is that? Well, the first row doesn't change. These entries in the first column below the diagonal have been eliminated. But as a result of applying row operations and updating the rest of the matrix, what we get is a 0 here, minus 9, minus 6, minus 12. So, so at this point, we've run into a problem. Gauss elimination cannot continue as is because we'd be dividing by 0 here. So now we have to, our next operation is to swap rows 2 and 3. So so this matrix right here that implements the row operations to eliminate the first column, that's actually M1 rather. So I go ahead and swap the second and third rows. Okay, and now there's no more row operations to perform because the matrix is already upper triangular. So that is our U. Okay. Okay. Actually, this matrix I can call, this is what I call A2. And then because we just did the swap and there's no more row operations, that is our A3 that we get from working on the first 2 columns. And that is our U. So just using a notation I've been using all this time. Okay. Now, what is the permutation matrix that affected this row interchange? Well, you're swapping rows 2 and 3. So for permutation matrix, you're swapping the second and third rows of identity. So that'd be 0, 0, 1, 0, 1, 0. So that's our permutation matrix. And you can confirm directly that this matrix is an orthogonal matrix. So P2 transpose times P2 gives you identity. All permutation matrices are orthogonal. Okay, so now, as a result of all this, we have our LU decomposition of the permuted matrix. PA is equal to LU, and now I can write out what everything is. So P is that one permutation, because all we had to do was swap rows 2 and 3. Okay. And then A is our original matrix. U is our resulting matrix, so we already have those written out. But here's, I think, the most interesting aspect of this example from a implementation point of view. What does our L look like? Well, here are the multipliers we had before. We had multipliers of 2 and 3 here, and then that's all we needed. But in our final PA equals LU decomposition, all right, it's unit lower triangular. We have nothing here because we didn't need to do anything. And the multipliers swap. So I actually have 3 and 2. So, so this is your final L matrix. So watch what happened. Here's the order in which we performed the row operations in the first place, 2, then 3. Because we had to swap rows 2 and 3 of A, we also needed to swap rows 2 and 3 of the L we were generating. and we see that in the final result. So that's why in the algorithm I put up last time, when I said you got to swap whatever rows due to partial pivoting, swap the entire rows, rearrange your multipliers as well as the rows of your matrix you're working on. And then everything works out. That's what makes this correct. So that's an important implementation detail that apparently I can't talk enough about. But it's how a lot of programs get screwed up from forgetting little details like that. Okay, so any questions about how we get this LU factorization with pivoting? All right, so as long as you make sure your multipliers account for your row interchanges, everything works. This works. Now that we have the whole process, now the thing is, this will work for any invertible matrix. Now that pivoting is included, because A might not have an LU factorization, but PA will. So now we have a full algorithm for solving AX equals B for any square invertible matrix A. All right. I want to check what's on the. Okay, so if there's only this writing here, is that visible at least?
Not at all.
Ugh.
Yeah, I can't see anything.
But the last board was okay.
Well, it was for the first like 5 minutes, then it started getting blurry again.
Yeah, what's kind of weird is that sometimes when I check the video, like the quality seems to go in and out. And is that what you've seen too, just sitting in on a call?
It's just been the beginning that's been good. This has been worse than it ever has.
Okay. Let's see. How much have we recorded now? Okay, so I'm going to do the same thing as last time. Just take a minute here to check the video.